that was not good. All right, so the record is on. All right. So we have a homework assignment. Okay, so if you go to CISP 440, I believe the homework assignments should be visible to you. So let me go there. I can show you what it looks like and what to do with it. So you go all the way down to, oh, okay, I got past that point. Nope, okay, right there. One more. There we go. So if you go to the graphs module, application of Dijkstra's algorithm as a homework assignment is released. So when you go there, it will give you a description of the homework assignment. I give you a set of all the vertices, V, a set of all the edges. Each one is a 2 tuple. The first item in the 2 tuple is where the edge is coming from, and then the second one is where it's going to. You also get a function D, but the function D is also represented as a set of two, quote unquote, 2 tuples. But each 2 tuple in D starts with an edge, and then the second item is a number, which is the distance of that particular edge. So if you are one of those people who's more visual, you're more than welcome to come up with, to draw the actual graph to help you in the process of doing this. I can see that as a double-edged sword, okay? Because if you're used to processing things visually, that means you may not be following the algorithm to the T, okay? Because to the T, because it's not a visual thing, right? You're following an algorithm is not a very visual thing. So that's kind of my caution. I just want to bring that to the whole class. And this is a spreadsheet that you can use as a template. So let me open up the spreadsheet so that you can take a look at what it looks like. So this one is just a template. So what you need to do is to go to File, and then go to Make a Copy, and then make sure that when you make a copy, that it is going to the folder that you own. Okay, so that part is super important. So click on the folder, because otherwise it will try to create it in the same folder and it's not going to work. So you want to create a folder in your own location, which is just navigate to My Drive and then select a subfolder over there. So that's my caution, because if you don't do anything and you say make a copy, it will not make a copy, and it may not give you an error message in the process too. So just be careful about that portion. It will ask you some permissions, because there's some scripts associated with this spreadsheet here. The script is here for a reason. I think some of you remember that last time I forgot about an update on one of these columns, and I was using the original value of one of the L values. So I made a tiny little script so that the last updated value, so let's say I just stick a 4 here, it is automatically updated here too. So that means you can scroll the bottom part any way you want to, but the most recent update of any column is always reflected on row 3. So hopefully that will help you a little bit. The other thing I also figure out is how to do a strikeout that is only partial. So let's just say that you type A, B, C, D, E, F, and you want to strike out just CD, just that portion. So the key to do that is to use the shortcut key, which is Alt-Shift-5. So that will strike out only a portion of the text. Unfortunately, it doesn't show here when it is on row 3. It doesn't show the strikeout, but it does show over here. So in case you want to use strikeout to show me that, okay, I'm removing this edge and I'm adding this edge over here, that's one way to do it. But it doesn't show on row 3. I should probably just make sure that this is not bold, okay, because and it will give you a warning. If you accidentally try to make a change to row 3, it will give you a warning, because I'm protecting that entire row so that people do not accidentally get rid of the formula that I have put in here. So is that okay? Are there any questions about how you're supposed to work with this sheet over here? Otherwise, the columns are pretty much the same as we set it up in the previous class. So hopefully that will work out okay with you guys. Yes? Okay, excellent. So this is a little bit more complex as a graph compared to what we talked about in class. So there are a few kind of situations that are by design tricky. But if you follow the algorithm, okay, if you just follow mechanically the algorithm, none of that is tricky, because you're running through the logic as specified in the algorithm. So I don't think it's going to be tricky from your perspective. But when you look at the actual graph, you draw the whole thing out, you go like, okay, that looks a little bit tricky. That is by design. Okay, so let me just get rid of this stuff here and this thing over here. All right. Are there any questions about what you need to do or how to work with this Google Sheet? Okay, all right. So that's all done. I'm going to close this. And now we can move on to the A-star algorithm. But before I move on to the A-star algorithm, are there any questions about Dijkstra's algorithm? No questions about that. Okay, all right, cool. So now we move on to the A-star algorithm, which is a kind of like, it serves the same purpose, okay? And, okay, I forgot to change this part here. Okay, I'll go ahead and change it first, okay, because that just looks ugly and I don't like it that way. I fixed the earlier one and I forgot to fix the other one. Okay, let me show you what is happening here and why it shows so in a way that is so ugly. It has to do with the use of the asterisk symbol. So the asterisk symbol normally does not need to be escaped when it is inside a math equation like here. But the processing of Markdown, using this tool, which is GitHub's own interpretation of Markdown, is a little bit flawed, okay? Because anything between two asterisks is considered to be emphasized, which is normally italicized. And so it is italicizing a whole section here between these two asterisks. So any asterisk that is not escaped by a backslash character is going to be a problem. So that's the issue with why the formatting looks kind of odd. So there are a few here, and instead of doing this by hand, I can now use find and specify anything other than a backslash followed by an actual asterisk. And this is a regular expression, so I can now just look for all the. So these two are intended, okay? Underestimate is supposed to be italicized. So these two, I'll leave them alone. This one, I still need to backslash or escape it. And then this one needs to be escaped. And there's a whole bunch. These two are supposed to be italicized. Through is supposed to be a word that is italicized, so they're fine. And the A-star algorithm, I think this one is fine because it's just in the header, so I don't think that's going to be an issue. And that's the one I didn't catch earlier. Okay. Let's see what. Okay, I think that's all. So now we just commit, give it a minute or two to rebake the markdown document back into the document. I can still use it like this, okay? This is still workable. So we can just kind of go with this one for now. All right, so this is the A-star algorithm. The main difference between the A-star algorithm versus Dijkstra's algorithm is that the A-star algorithm relies on what we call a heuristic in order to reduce the complexity, save time when it comes to trying to find the shortest path. So there's nothing wrong with Dijkstra's algorithm in terms of correctness. It will find the shortest path, but it might go to places where you go like, why are you exploring these options? There's no way the shortest path can be over here. And Dijkstra's algorithm will do that, okay? So the best way to illustrate why it works in that particular way is to take a look at the map of the entire United States. So I'm just going to go to maps.google.com and zoom all the way out, okay, until we have US continental displayed here. Okay, so let's just say that you're somewhere in Kansas and you're trying to find the shortest path to San Francisco, okay? Dijkstra's algorithm, let me see. I will reverse the whole thing because I changed the algorithm because it will explore from the destination and expand it outward. So we'll just say that you're in San Francisco, this is where you are, and you want to go to some place in Kansas, okay? And the Dijkstra's algorithm that we have talked about will start from the destination or the destinations if they're multiple, and it will expand those, in a if you imagine it on a map, it's going to be in a concentric way, more or less. So that means it will immediately, try to explore, whatever city you want to explore, you want to get to in Kansas, and then it'll explore, the entire Kansas, and then it'll explore Colorado, Nebraska, Missouri, and Oklahoma in order to find the shortest path from San Francisco to Kansas. You go like, I think we can skip Missouri. I'm pretty sure the shortest path does not need to go to Missouri and then double back to Kansas, right? But that's not how Dijkstra's algorithm operates. It would expand the circle in a concentric way until it touches the origin, the point where you're starting from. So that's the modified Dijkstra's algorithm. The original Dijkstra's algorithm will start exploration from the origin until it touches the destination. Nonetheless, it is still going to do the same way. It will still expand in concentric circles in a way, if you were to look at it in a graphical way, it will still be expanding in concentric circles, which means it will still be exploring a lot of places where you go like, why are you exploring that path? There's no way the shortest path is over there, but it will do it. Is that okay? Does everybody understand, why it is not the smartest way of doing things, even though it will find the shortest path? So that's Dijkstra's algorithm. The A-star algorithm is a little bit different. Now, because of the use of a heuristic, the A-star algorithm does not find multiple shortest path from any vertex to any destination. It cannot do that. You have to start with a point of origin. This is the start vertex. And then you have to designate a single destination and go like, this is where we want to end up at, okay? But the way it works is kind of interesting. So the way it works, so let's say we are going from Kansas all the way to San Francisco this time because of the way the destination and the origin has to work in this particular algorithm. So the way it works is it will start from whatever city you're starting from in Kansas. And then it will go to a particular place, let's say the border between Kansas and Colorado. It will figure out the shortest path from here to the border. And then it will estimate from the border between Colorado and Kansas all the way to San Francisco. It will use a non-overestimate, okay, as quote-unquote a heuristic. So what that means on a map is simply, let's go ahead and draw a straight line from here all the way to San Francisco, and we'll just use that as a rough estimate of the number of miles that you have to drive from here to here. Now, is that a completely accurate estimation? No, probably not. Because the highway goes up and down, and it has to go around curves and whatnot. But it is an estimate. Okay, so that means if I were to go to the border between Kansas and Missouri, and we say, okay, so this path I know the exact distance, and then this part here is just an estimate. It will still come to the conclusion that I don't think we are going to go to Missouri to find the shortest path from Kansas to San Francisco. Okay, so that's the contribution of the heuristic function, which is giving us a general guidance of evaluating possibilities and go like, does this even seem like a good possibility? Does it seem like the shortest path is in this direction? And the heuristic function can basically rule out a lot of possibilities because it just doesn't make sense. Now, what is the heuristic function? How do we compute the heuristic function? That all depends on what you're dealing with. So in the case of a map like this, the actual straight line distance between two coordinates will serve as a pretty good heuristic function, okay? Because it is not going to overestimate for sure. The only time it will overestimate is when we have wormhole technology. But since we don't have wormhole technology, we're fine, okay? So it has to be not overestimating, and it has to be relatively easy to compute. But if you're given two coordinates, okay, like the center of Kansas and the coordinate of some place in San Francisco, figuring out the number of miles of a straight line between those 2 points is not very hard to compute, okay? So that's why, in this case, okay, the the distance of a straight line between 2 points is a fairly good heuristic function. Is that okay? So heuristic function is also called a rule of thumb. And when a heuristic function does not overestimate, it is also called an admissible heuristic function. So the word admissible has a very special meaning in this context. Are we good so far with just those terms? Okay. So now we stop looking at this map, and then we look at an example. So at the very end of the slide, I made a new example. So this is our new example just for A star, because the dotted line is giving us the heuristic value or the heuristic function from every vertex to the destination. The destination is vertex F in this case. So we have a whole bunch of vertices, A, B, C, D, E, F, and I thought I had a G, but nope, there's no G. So A, B, C, D, E, F are the vertices. So the solid line are the actual distances. So that means from A to C, it's going to cost me 5 units in order to go from A to C. From C to B, it will cost me 2 units of whatever. The dotted line, on the other hand, are the heuristic estimates. So for no particular reason, okay, for no particular reason, the estimate from vertex E to vertex F is 13, which turns out to be the actual length of the shortest path. So in other words, a heuristic, even if it is to be admissible, can be exactly the length of the shortest path. Okay, that is still okay. But then you can also see some underestimate, like from vertex D to vertex F, the heuristic value is only 0. Well, is it okay? You have to ask two questions. Well, one question. Is this not overestimating the actual distance of the shortest path from D to F? Yeah, it's not overestimating, okay, because no edge can go negative, which means the length of any path cannot be negative. So 0, it's not going to be overestimating anything. Is that okay? Now, is it a good heuristic value? The answer is no, by design, because I want to trick the A star algorithm to explore things that it really should not be exploring. Okay, so I designed this particular graph to have heuristic values to trick the A star algorithm to go places where you typically don't want it to go. But as long as the heuristic values are not overestimating, it will still find the correct answer. In other words, it will find the shortest path. Is that okay so far? All right. So this is what we'll be working on today using a spreadsheet, kind of like what we did on Monday. But before we do that, okay, let me just kind of go back to the proper web presentation. It's not much better, but it is a little bit better. All right, so I'll go ahead and explain the algorithm first, and then we'll go in and actually talk about how do we follow all the steps in the algorithm. All right, so the first part is what is given to us. Okay, what is given to us is a graph. A graph has 2 components: a set of vertices and a set of edges. So when we talk about these algorithms, the graphs that we talk about are also called digraphs, D-I-G-R-A-P-H, which is the abbreviation of directed graph or directional graphs. So every edge has a starting point and an ending point, but it's not bidirectional. Now, can I have vertex A go into vertex B and have vertex B to go back to vertex A? Yes, you can do that. But can I have different distances associated with those 2 different edges? The answer is also yes. Okay, it doesn't have to be symmetrical. So why do we want to have graphs that are directional and you cannot just simply go like, oh, I can go from here to here, but automatically I can reverse the direction? Because this is more general. Any graph that is bidirectional can be represented as a directional graph. You just have twice the number of edges, okay? But the other way around is not possible, okay? And then if you think about places like San Francisco, why do you think digraph makes a lot more sense in San Francisco than, say, in some other smaller cities in the United States? Yeah. They have a lot of one-way streets. Yep. And not only that, okay? And not only that, The amount of time that it needs in order involving a path that has a lot of left turns is actually significantly higher compared to a path that involves only right turns. Especially when in a city like San Francisco, where there's a lot of traffic. There was one episode of what was it? Um, what was the name of that show that where there are two people and they're always doing some fun experiments? Mythbusters, that's right. So there's one Mythbuster episode where they were talking about, does it make sense to make a bunch of right turns instead of left turns, even though the left turns lead to a shorter path, and then the right turns take you around a whole block? Does it still make sense to make a, a left turn, make a bunch of right turns instead of making a single left turn? And it was interesting because it depends on what you're driving. That was their conclusion. Because if you're driving an EV and you're only looking at the cost in terms of energy, it's not a big deal with the EV, okay? Because you're just sitting waiting for the left turn signal, okay? And okay, you might be running your air conditioning, the headlight may be on, but it's still not a whole lot of energy, of expense, not a whole lot of expense. When you're running a diesel truck, turns out the fuel that is burned when you are just waiting for the left turn is significant. So that was it was interesting. That's what I learned from that episode of Mythbusters. Yep. So anyway, I was just trying to get to why we want digraph or directed graph as opposed to bidirectional graphs. So that's the reason. Anyway, getting on to the distance function, which is the same as the distance function for Dijkstra's algorithm. We still need that, okay? We still need to know what is the distance of the edges of each and every one of those edges. Unlike Dijkstra's algorithm, when we are working with the A-star algorithm, we want a single source or a single origin. In this case, I use lowercase s, which has to be an element of the vertices because it has to be a vertex. But this is the starting point, okay? And we want a single vertex as the destination. And because x marks the spot, so I use variable x or the symbol x to represent the destination. Is that okay so far? So the job, or what we want to do, is to start with vertex s, and we want to end up at vertex x, and we want to do that using the shortest path possible. So one more thing that is also different is this time we also have available to us a heuristic function. So what the heuristic function does in general is you can give it any pair of vertices and it will give you an estimate of how, what is the length of the shortest path between those two vertices. But in reality, we only care about from any vertex to the destination vertex. Okay, so that means this is it's nice to have this function kind of structured this way, but in practice we really only need the destination as the only destination in this Cartesian product. Is that okay? So even though you can have this one, but the part of this entire function that is relevant to us to solve this problem only needs to have the vertex x as the only item of the Cartesian product. Okay. All right, so now we move on to the initialization. So this is the part when I kind of have to explain what each symbol is representing. So for each v, so v is really just a variable in the loop. So for every v as a vertex in the set of vertices v, uppercase V, initialize as follows. If v is not the origin or the start vertex, then this is how we're going to initialize g of v and f of v. G of v is initialized to infinity because g of v is the actual length of the shortest path known up to a certain point from vertex s to vertex v. In other words, we start from the start vertex and we are asking, okay, what is the shortest path from the start vertex to this particular vertex v? That's what g of v is representing. F of v is also initialized to infinity. F of v is the estimation, in this case, of the length of the shortest path from the start vertex through vertex V, which is the parameter here, to the destination. So one is an exact length of the shortest known path up to a certain point of the algorithm. That is G of V. The other one is that, okay? It is the exact length of the shortest known path from the start vertex to vertex V, but we're also adding an estimate from vertex V all the way to the destination using the heuristic function. So that's why the way we work out f of v is g of v plus h of vx. So once again, okay, the two components. The first component is the actual length of the shortest known path from the start vertex S to this particular vertex V. The second component is more of an estimate, okay? This is estimating from vertex V to vertex X, which is our destination, what is an estimate? And that cannot overestimate, it can underestimate, but it cannot overestimate. So that's what happens when V is not the start vertex. If V is the start vertex, then it's easy, because all we need to do is to say, hey, what is the length of the shortest path from the start vertex to itself? What do you think? 0, okay? So now we just have to work out what is f of v. It is h of sx, because we are looking at the heuristic value starting from the start vertex, ending with the destination, which is known as vertex x in this case. So are we okay with the initialization of the g and the f values? Okay, all right. So prev, it stands for previous, okay? So in other words, we're maintaining a back pointer in this case. So the back pointer is useful in this case because we hopefully will eventually end up at the destination, because we're starting from the start vertex and hopefully we'll end up at the destination. The question is, when we get to the destination, what is the actual path from the start vertex to get to the destination? So prev, or previous, is helping us to keep track of how did I get to this particular vertex from the start vertex. So when we have the prev all the way up to the destination, then we can follow these back pointers to all the way back to the source, back to the start vertex, and that's how we can figure out the actual shortest path from vertex S all the way to vertex X. So when we actually track the algorithm, we'll actually see how that works. So the rest of the algorithm has some of the elements of Dijkstra's algorithm, and some of this is also a little bit different. O as a set is kind of like the boundary set. The job of set O is similar to the job of set Q in Dijkstra's algorithm, but the direction is different because this one starts with a start vertex, the other one starts with all the destination vertices. So this one starts with a single element in the set, which is our start vertex. And then the algorithm goes like this. So this time, I am not even caring whether O is empty or not. Okay, so O does not have to be empty in order for the while loop to exit. The condition to stay in the loop is this condition here. So once again, it is a quantified expression, and hopefully by this time, we have developed the skills to read quantified expressions. So let's go ahead and take a look at this one and say, okay, what does that mean? So this is an existential quantifier, which means I need to find at least one element V in the set O such that f of V is less than g of x. What does that mean? Well, we'll look at each component individually and try to find out what does it mean? Okay, I know how to read it, okay? But what does it mean and what is the importance of this condition? So we want to try to figure that out. So in this case, let's take a look at each symbol. What is g of x? According to the definition of g of x, specifically x in this case, is what? It is the actual length of the shortest known path doing the rest. From where to where? That is correct, okay? But x is the destination. So g of x is simply the length of the shortest known path from the start vertex to the destination vertex. That's basically it. Okay. So this means, okay, I might have found a path already and it has a length of this. Now, is that really the shortest path? I don't know, maybe not. Okay, it is entirely possible that the first path that you find from the start vertex to the destination is not the shortest one. Okay, but it has a length. Okay, and this is that length. What about f of v? What is it representing? Now, v can be any vertex, right? So what is f of v according to the way we define f of v a little bit earlier? You can actually see what f of v is representing. So f of v is representing an estimate. Okay, it is always an underestimate, or it cannot be overestimate. It can be exact. So it is an estimate of the length of the shortest path from the start vertex going through vertex v and then going to the destination. Is that okay? So it is just an estimate, okay? And it cannot overestimate. This one has to be always either underestimating or it is exact. So what is the significance that we find this less than? In other words, what if all the elements in O, all the vertices in O, have their f values greater than or equal to g of x? What is that representing? What is that telling us? That exactly, that we have found the shortest path. And the other way to say that is all the other alternative paths cannot be shorter than the one that we have found already, because f of v can only be underestimating or it cannot overestimate. So if f of v is already greater than g of x, then there exists no path from the start vertex through vertex v to the destination that can be shorter than g of x. And that is by the very definition of how we define f and g as functions. Is that okay? So, okay, taking a step back, what that means is this condition here means there is still hope that we can find a shorter path. That's basically what this entire quantified expression is saying, is there's still hope, okay? But are we really sure that we can find another path that is shorter than the one that we have found already? There's no guarantee. It simply means that, yeah, there's a possibility. But if this condition is false, that means there's no possibility. Okay, all the remaining paths to be explored will have a length that is greater than the one that we have found already. Are we doing okay so far with that? Okay, so just that line, okay, just looking at this one single expression involves quite a few things. One is reading quantified expression, but the most important part is how do we interpret the quantified expression. You can read a quantified expression mechanically, okay? Mechanically, I know what it means, but how does it connect to the purpose of this algorithm and what is the significance of that expression in this algorithm? That takes time, okay? That takes a little bit of time of thinking, analysis, and go like, okay, I want to make the connections between this expression with what we are trying to do here. All right, so the next line, which is let C as an element of O such that blah, 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 blah. So this one is kind of like the second statement or the statement right after the while in the Dijkstra's algorithm. We are selecting one vertex out of all the vertices in O, and that would be the one that we are quote unquote exploring, okay? And once again, this is also a greedy algorithm because we are looking for the most promising candidate. So let's check out, what I mean by the most, promising candidate. So the way we choose this C over here is to make this quantified expression true, okay? What does this quantified expression is trying to say? All it really is saying is f of C amongst all the f values of vertices in O, C has the lowest of all the f values of the vertices that are in O. So we're looking at the most promising candidate because according to the estimates, this particular vertex C has the shortest estimated length of path from the start vertex through C all the way to the destination. It is the most promising. Are we good so far with the reasoning behind, how we choose vertex C out of O? Okay, now C is just a variable name, so later on we have actual vertex C. So this one is just a variable name. It is not saying exactly vertex C. It is basically choosing that vertex so that the value of this variable is that particular vertex. So just like with Dijkstra's algorithm, once you have chosen which one to expand or explore, however you want to call that, we have to remove it from set O so that we don't have an infinite loop. And then just like with Dijkstra's algorithm, looking at all the incoming edges to the vertex that we have chosen, now we are looking at all the outgoing vertices from the vertex that we have chosen. So we have chosen vertex C, so now we are looking at all the edges starting with C but going to some neighbor of C. But because N is the second item of the two tuple, so we are looking at outgoing edges from C. So is that okay? Does everybody understand what I said, what I meant by outgoing edges from C as opposed to incoming edges to C? That part okay? All right. So we'll go through a trace just like what we did on Monday with the graph that I have constructed later on. So this time, okay, so there's a little bit of inconsistency here because this time I use a local or temporary variable t, just so that it's easier to kind of describe what we're comparing, but it's kind of the same thing. All right, so let's take a look at g of c plus d of cn. What does that mean? What is g of c? G of c is the length of the shortest known path up to this point from the start vertex to exactly just vertex C. That's what it is. So what if I add the distance of the edge Cn to g of c? What do I end up with? How would you describe the sum between g of c and d of cn? Yep, it is the length of a path, right? We don't know whether it's shorter or not, but it is the length of a path from the start vertex going through vertex C and then to vertex N. Is that part okay? All right. Okay. Is it a shorter path? We don't know yet, okay? Not on this line. But on the next line, we'll make that determination. Because if t is less than g of n, then by definition of g, we have just found a shorter path. Does that make sense? Because t is basically an alternative, g, I take it back, sorry. T, local variable t, is the length of an alternative path from the start vertex through C to vertex N. Now, if it ends up to be shorter compared to the currently known length of the length of the currently known shortest path, then I have just found a shorter path. So if I find a shorter path, then there's a bunch of stuff that I need to do. But those are very similar to what we had to do with Dijkstra's algorithm. First, well, guess what? N is getting a shorter path, or I just found a shorter path to vertex N. Let's put it into the set O. In other words, it becomes a part of, quote unquote, my boundary, okay, of exploration. Then we go like, okay, how do we get to N again? Oh, we went to N from vertex C. So the previous of N, the back pointer of N is C. Is that okay? So that's just for me to kind of keep track of how did I get to the destination, if I get to the destination at some point. And then we also want to update g of n, because g of n by definition is supposed to be the length of the path that is known up to this point. Guess what? I just found a shorter path. So let's update the length of that path to t. And then finally, we also update f of n. Now, strictly speaking, f of n is not really required because you can always compute f of n from g of n and the heuristic from n to x. So that can always be computed on the fly. But if you compute this all the time from scratch, you're just kind of recomputing a lot of values unnecessarily. So instead of wasting computational time, I'm just using a little bit more space in memory to remember what is the estimated length of the path from the start vertex through n to the destination. So that's the only purpose why we are keeping track of f of n. It can be computed on the fly every single time, but it's not. It's kind of expensive to do it that way. All right. So when the loop exits, after the loop exits, then we go to here where we define a new graph. So the new graph, hopefully, will be a single path from the destination back to the start vertex. And the way it is constructed is simply to follow all the back pointers until we get to the origin. So we'll worry about this after the whole thing is solved. All right, so are there any questions regarding the algorithm itself? When I ask you questions about the algorithm itself, I think at this point it is best to focus on why do we have this statement here? What is the purpose of this statement? So do we have any questions along that line at this point? Mm-hmm.
Can you describe the last part again?
Hmm? The last part here? Okay, so let's take a look at this one. For all the W in V, okay, in other words, for every vertex, try to do the following. If the previous of W equals V, the previous of W equals V if and only if WV is in the edge of the set of edges from the start vertex to the destination vertex. So that's basically what we are doing here. We're reconstructing a new graph that has ESX as the set of all the edges. The vertices will still be the same. You can see the new graph has the same set of vertices, but the set of edges will be a little bit different. It's based on all the previous pointers.
You're saying you update the E?
So this is, okay, this does not procedurally tell you how to construct ESX, but it tells you about the qualification of members in ESX. In other words, we look at all the possibilities, we look at all the W's, and then we say if the previous of W is some kind of V, then VW as an edge has to be in ESX. So it's not algorithm, it doesn't give you the method to create ESX, but it tells you about the qualifications of who should be in ESX. Yep.
For the G function,
Mm-hmm.
so it,
The lowercase g, right?
yeah,
Yep.
it gives the shortest path to from the start vertex to the vertex that we're looking at.
Yes.
How does how do we find a path, like a new shorter path to N other than G of N?
We'll see. Because I constructed an example where we will basically revisit the same vertex several times. It's like, oh, we found the shortest path from here to here already. Cool. Wait, there's another path that is even shorter. And there's another one even shorter. So we'll be updating things quite a few times, because I constructed the example that I was presenting a little bit earlier. That one was constructed so that we have to update multiple times. So that should illustrate what you were asking. But keep that question in your mind just in case I did not fully answer that question. All right. So are we ready to kind of do a hand trace of all this stuff? Okay. All right. So what I'll do is I am going to the shared folder for this class. That's not for this class, that's for all my classes. So we'll go to here, go to shared. I'm just trying to be lazy and just kind of reuse Dijkstra template because of the ability of the third row to reflect the most recent value. That's actually quite helpful. So I'm just going to make a new version of this, make a copy. All right. There we go. Double click. And we'll call this, the A star template. And then make a, well, okay, I'm just going to populate this one and then later on turn it back into a template. So instead of Q, we have O, and then choosing, instead of C, instead of V, we have C, and then this is neighbor N. Instead of E prime, we don't have E prime anymore, so the entire column D is gone. So get rid of column D. delete column. And now we have, we don't have L value, we don't have G either. So I would just kind of delete that one. And instead of L, we have G function. And then we have a bunch of things like that. Okay, so let me see if I can copy and paste this. Copy and paste. Oh, okay, it works, kind of. Because we have G, we have F. Okay, let me shrink the columns first, because this one is a little bit more involved in terms of how many things we have to track. So I'll fix all of that later. And then we have one more, because we also have to track previous. So now we have prev, P-R-E-V, and adjust column width. There we go. All right. And then I need to fix all the data here. There we go. All right, so that looks good, looks good, looks good. So last value, for those of you who are kind of asking, what is last value? It is not built into the spreadsheet. I had to write my own little tiny little function here to find out what is the last defined value of a column. So that's basically what last value is. All right. So let me just refresh the whole screen, because A is not supposed to be loading. We got nothing right now. All right, so let's do the initialization. And AB should not be bold-faced. Okay, so we get rid of all the boldface, Control B, like so. All right, so let me switch back to the module and go all the way to this map here. We'll shrink the screen a little bit, just so that it doesn't take up the entire screen. Probably, is this scale okay? Can people in the back still be, okay, all right, so we'll take a snapshot of this. And open it with this tool and make it always on top. So this way we don't lose track of this as we try to follow the algorithm. And here we go. All right. So perfect. Okay. I did not design it this way, but perfect. All right. So we have to do a bunch of initialization. The initialization of G and F is kind of like G is easy, because the only destination, which is vertex F, is the only one that has a 0. Because when you're already, no, I take it back. It has to do with the origin. So in this case, A is the origin, not E. Okay, so A is the origin. So the origin has a G value of 1, which I should not be updating here. I should update this one. So let me go back here. It is a 0, but everybody else are infinity. Because I have to remind myself that we are starting from the origin or the start vertex and not from the destination. Because that's how we did things in Dijkstra's algorithm, but with this one, it's the other way around. All right, the F value is the heuristic value from A all the way to F, and the dotted line is representing the heuristic value. So this one is 5, so I put 5 over here, and then everybody else would still be infinity. So copy and paste. And for the previous value, everybody has undefined. So I'm going to use UND to represent undefined, and that applies to everybody here. All right, so are we good so far? Okay, and O is initialized as a set with just the start vertex. The start vertex in this particular problem is vertex A, not vertex E intentionally. So we'll look at this, and say, okay, we're starting with vertex A here. All right, so when there's only one vertex, how do you choose which one to expand? Well, first of all, do we even want to go through one iteration? In other words, the condition that says at least one vertex in O should have an F value that is less than the G value of the destination. The destination in this case is vertex F, okay? So let me just highlight F because that's our destination. So what do you think? We are not done yet, right? Because f of a is a 5. G of f, which is our destination, is infinity. 5 is less than infinity. Seems true to me. So that means we have to go into the loop. So I'm not double backing between this screen and the algorithm. So I'm just describing what the algorithm is supposed to do. So now we have to choose one of the vertices from O to be to fill variable C. Well, this time is super easy, right? Because we only have one vertex and it meets the minimum requirement to continue with the loop. So we're just going to take, okay, let's pick A, and then the set O becomes empty at this point. And now we have to look at all the outgoing edges coming from vertex A. So having a graphical representation kind of helps, right? Because we can now look at, oh, okay, so A goes to B, A goes to C, and A also goes to D. So once again, the ordering of which outgoing edge to explore first is not important. So you guys can tell me which way you want to go about doing this. Tell me. B, C, D. Binary, okay. Binary coded decimal. And I'm not kidding you. BCD actually means binary coded decimal. And for those of you who ask, so what does it mean? What is binary coded decimal? That seems like an oxymoron to me. Is it binary or is it decimal? You don't want to know the answer. Okay, look it up yourself from Wikipedia because you're not going to like the answer. So I hate to be the person who tells you something, they go like, ew, that is yucky. Okay, so anyway, so we start with B. And the evaluation is, I look at vertex B, which is right here, and I ask, if I were to go through vertex A, then we go to vertex B, what is the length of that path? Well, that's easy because G of A is 0, and then the actual distance of this edge is 8. So that means I would have found a path that has a length of 8 from vertex A, the starting point, to vertex B. Okay, so T, okay, fine. I need one extra column to represent T. So we'll just go ahead and make a T over here. No, I want it to be on the other side. So we want it to be insert one to the right, not the left. There we go. All right, fine. We need one more column here, and extend this so that we can take a look at the last value, which is not even important in this case. So, nope, that's not supposed to be there. Okay, now we can backfill T. So T is 8. So now the question is T less than G of B? G of B is infinity right now. No, just focus on row 3. Okay, row 3 will tell you the current value of each column. So G of B is infinity. T is 8. Is 8 less than infinity? Okay, so now we have a whole bunch of stuff to update. So we have to, yeah, go ahead. Did I? Oh, right. Okay, because it doesn't show, does it? There we go. Excellent. Thank you. So now we update G of B to be also 8. The order of the update is not really that important, okay? Except, once you determine G, it's easier to determine F. So can someone tell me how I should update F of B? F of B is defined to be G of B plus the heuristic value from vertex B all the way to the end, to the destination. So from what you can see on the graph, what should be F of B? Yep. So that would be 8 plus the heuristic value from B, which is 2, to F. So it'll be 10. Is that okay? All right. So then we got like, okay, cool. And then we have to update the previous. In other words, now we are saying in order to get to B, okay, because we're exploring B, so we must have found a way to get to B. So how did we get to B? Well, we got to B from A. Are we good so far? All right. So that's all the update, except I have to add B to the set O. So we have to include that. So now we look at vertex C. And we first compute T, and T is G of A plus the distance of the edge AC. The distance of the edge AC is a 5. G of A is a 0. 0 plus 5 is a 5. Is that less than G of C right now? G of C right now is infinity. 5 is less than infinity. It's true. So now we have the same kind of update as last time. So G of C is now updated to a 5. F of C is updated to be the 5 plus this one over here, which is now a 6. And in order to get to C, we are also coming from A. And then we also have to remember to add C to the set O because the G value of B just got updated. That's basically the trigger. Are we good so far? And now we move on to the outgoing edge AD, and we consider D as the next door neighbor of A, and then we do the same computation. G of A is a 0. 0 plus 2 is just a 2. And then we say, okay, is 2 less than infinity? Yep. Let's do a bunch of updates. 2 goes here, and then 2 plus the heuristic value, which is 0, is also just 2. And to get to vertex D, we are also coming from vertex A, and we also want to add vertex C to the set so that it is now, we now remember, it's like, okay, we just updated the G values of B, C, and D. Maybe one of them will show us the shortest path to the destination. So are we good so far? We are done with the for each loop inside the while loop, which is the last item in the while loop. So now we have to go back to the beginning of the while loop. So are we good so far? Are we kind of still tracking the algorithm? Okay. So it would help if you can have a mobile device or a printout of the algorithm, so it's easier for you to kind of read the algorithm on your part when you're following my kind of instruction. Okay, so now we go back to the while loop, and the condition of the while loop is asking, is at least one vertex in the set O having an F value that is less than the G value of the destination, which is vertex F in this case? The answer is simple, okay, because G of F is still in infinity, okay, and all the F values, the F value of something in the set O must not be infinity, because otherwise we would not have put it in the set. So that means the answer is a clear yes. Okay, but now the difficult part is how do we choose which one to expand? In other words, what is variable C this time? Which vertex out of B, C, and D looks the most promising? So we look at the F value. We don't look at the G value. We look at the F value. So we go like, oh, okay, the clear winner is vertex D. Okay, so we pick out vertex D, and then we ask, okay, vertex D, okay, take it out of the set, which means I have to remember to update the set and take D out of it. So now the question is, okay, from D, what are the outgoing edges? D has 2 outgoing edges, one going to C and one going straight to F. Okay, so do you want to explore C and then F or the other way around? It doesn't really matter. Okay, C and F. Okay, fine. Okay, so now we go for C first, right? So now we are asking what is the length of that path of the start vertex going to D, which is the length of that path is represented by G of D, which is a 2, plus the edge from D to C. From D to C, there's a path of 2, or the distance is 2, so that means we have a 4 here. So once we have T figured out, then we ask, is that a shorter length compared to G of C? So G of C is 5, and the answer is, yep, we just found a shorter path. So we have to update a bunch of stuff again. So this is now 4. This is 4 plus the heuristic value, which is what? 1. So 4 plus 1 is a 5. And we also have to update the previous of C, because instead of coming to C or reaching C from vertex A, we now go like, let's go from D to C. Is that okay? Because this is important, because now we are basically correcting, quote unquote, correcting a mistake that we made earlier, which is, oh, that was not really a good path to go to C. Let's go to C from D instead. So that means we also have to add vertex C to the set, but it has it already. So that means, there doesn't seem to be any change over here. Then we do the same thing with vertex F. So G of D is already a 2. DF as an edge has a distance of 20. Oh, am I correct? Nope. Nope. Okay. Right. Okay, this is correct. Never mind. So D to F is 20. So that means it is a 22. Okay. So this 22 is representing the length of a path starting from the start vertex to D, which has a length of 2 to begin with, and then from D to F. So from D to F, we have this edge that has a distance of 20, which is really bad. So together, it is a length of 22. Yes. 22 is the wrong. Oh, right. It's supposed to be here. Thank you. So now we ask, is this representing a shorter path to get to vertex F? In other words, we compare this 22 to G of F. As bad as it seems, yes, it is quote unquote a better way because we haven't found a single path to the destination up to this point. This is the first time we actually find a path to the destination. We go like, yay, we found a path. And then the F value of, excuse me, yes, the F value of vertex F is also just 22 because it's the destination. So the heuristic of going from F to F has to be a 0. And then for the first time, we go to the previous of F and go like, yes, we just found a way to get to you through vertex D. And now we add F to the set. You go like, but wait, hold on a second here. F is the destination. It doesn't make sense to add it to the boundary set. That's what the algorithm specifies, okay? It does not hurt, okay? So it is okay to treat the destination just as any other vertex, okay? It is not special in any way after the initialization, okay? So that's kind of the neat part of this algorithm. All right, so now we're done with the for loop, and then we go back to the beginning of the while loop, and then we ask, out of these three, does any one of these three have a f value that is less than the g value of the destination? Well, the g value of the destination is 22, okay? It is not infinity anymore, so now this time we have to be kind of careful. We look at the f value of b, it is a 10. We look at the f value of c, it is a 5. You go like, I think, yes, first of all, we continue with the loop. We cannot exit yet because both 5 and 10 are less than 22. We're looking at this 22 here or this 22 over here. And 2, to select which one to explore next, we have to find the one with the smallest value. F of C is a 5. It is the smallest between the B, C, and the F. So we're going to choose C to explore this time. So we take C out of the set. Okay. Like so. And then we look at the outgoing edges of C. C has 2 outgoing edges, one going to F, one going to B. Which one, what is the order that you want me to go over? Huh? F and then B? Okay, we can do that. So F and then B. All right, so what is the value of T if we are to go from the start vertex through vertex C to get to vertex F? So we look at G of C. G of C is currently a 4. And then the edge CF has a distance of 10. So 10 plus 4 is a 14. So 14 goes here. So now the question is, how does this 14 compare to the current G of F? The current G of F is 22. 14 is less than 22. We go like, aha, cool. We just found a shorter path. So put 14 over here. Put 14 over here as well because the heuristic to go from F to F has to be a 0 because that's our destination. And then we update the previous and go like, you know what I told you earlier to go to the destination from vertex D? Let's fix that. That's not the shortest path anymore. Let's go through C. Okay? But because we are doing this, we also need to add F to the set O, but it's already here, so it is as if nothing happened. Are we good so far? All right. So now we go to vertex B, okay? So we are now looking at G of C, which is a 4, and then we look at the distance of the edge CB. So CB has a distance of 2. 4 plus 2 is a 6. Okay, so we put a 6 here. And then we ask, did we just find a shorter path from the start vertex to vertex B? Currently, the length of the shortest path has 8. Now we have 6. Yep, the answer is yes. We just found a shorter path. So now we have another bunch of stuff to update. We put a 6 here, and then we put 6 plus the heuristic value from B to the destination, which is also 2. So that's an 8 over here. And then we update the previous of B and say, okay, instead of going to vertex B from vertex A, let's go through vertex C to do that. So that's a C over here. And then we also have to remember to add vertex B to the set O, but it's already there, so it is as if nothing happened. Is that okay? So is everybody kind of convinced that I engineered all of these heuristic value just to do extra work? Okay, I'm hoping that you guys got that sense. It's like, why? Yes, I engineered those heuristic value to so that we can do the extra work, so they can actually see things updating. It's like, we found a path already. Wait, but that's not the shortest path. Let's fix that. Okay. So now we look at the 2 vertices in O right here, and then we ask, is that condition for the while loop still true? In other words, is at least one of these 2 vertices having an F value that is less than the G value of the destination, which is F. So you have to remember the G value of F has been updated. We have been updating it. It is now a 14. The F value of B is an 8 right now. 8 is less than 14. So that means, yeah, we still have the potential of finding a shorter path. Is it a guarantee that we'll find a shorter path? No, but it can potentially exist. Okay, so now we go like, we are not done yet. Now I have to choose between those 2 based on just the F value. The F value of B is 8. The F value of F itself is 14. So we're going to choose B. So we take B out of the set. And then now we look at the outgoing edges of B. It has one single outgoing edge to F. So this time we don't really have a choice. So we just have to see, if we are to go from the start vertex through vertex B to vertex F, what is the length of that path? G of B currently is a 6. So that means we're looking at 6 plus the 2, because from B to F has a distance of 2. So we end up with what? 8 over here. And now we compare this 8 with the current value of G of F. Okay, so G of F is currently a 14. 8 is less than 14 is true. So now we go like, again, we found another shorter path. The answer is yes, we found yet another shorter path. So this is the 3rd path that we have found. So now we have to update a bunch of stuff. This is going to be 8. This is going to be 8. And we have to fix and go like, in order to get to the destination, don't go to the destination from vertex C. Go to the destination from vertex B instead. And we just updated the G value of F. We have to add F to the set, which is already here, so we don't end up doing anything. So now we are at the beginning of the while loop again, which means we evaluate the vertices in O, and we ask, is at least one of these vertices in O having an F value that is less than the F value of the destination? Well, the F value of the destination, which is G of F, is 8 right now. The F value of F is also 8. 8 is less than 8 is false. So we are done with the while loop. We are all done. Is that okay? So we have found the shortest path. The length of the shortest path is clear that it is just 8. Okay. Now the question is, um, how do we actually plot the shortest path? So the way mechanically, in terms of algorithm, the way you do it is to follow the back pointer. You start with the destination. The destination says, oh, okay, to get to me, you want to go to B. So you go to B and you say, okay, how do I get to B? Go through C. And then you go to C and go like, how do we get to C? Go through D. And then you ask, how do we get to D? Go from A. So that's how we figure out the shortest path. The actual path is going to be from A to D, and then from D to C, from C to B, and then from B to F. So as it turns out, in this particular case, the path that has the most number of hops, in other words, the most number of edges, turns out to be the smallest one. And we didn't find it until we have explored all the longer paths first, because I engineered the heuristic values to make sure of this kind of thing to happen. All right, so that's kind of the conclusion of the A star algorithm. Do we have any questions about the trace or the rationale of the algorithm itself? So I can show the algorithm. So if you want me to switch back to the trace, that's fine too. So the algorithm is specified here. Let me go back to zoom in a little bit more. The actual algorithm is really short. The actual algorithm is from this while, and that's the only loop. This part here is just reconstructing the shortest path, which we just kind of did, you know, just kind of manually following the edges. Yep.
On which part does it, or if you could go back to the spreadsheet real quick.
Sure. Yep.
On which part does it say that if you already visited the vertex and then you want to like put it back into O to not put it back in, like on line from line 14 to 15?
From row 14 to 15.
Like we didn't put B back in.
We did put B back in, but B was there already, so it does not appear that we have made any changes. Because B was put in there really kind of early on, but it stayed there because it never looked promising to us. And it never looked promising to us because I engineered the heuristic value so that the actual longer paths look more attractive than the actual shortest path. But that's all engineered. That's completely my doing of forcing the algorithm to go through a lot of things just to find out, okay, that wasn't really the shortest path. That wasn't the shortest path either, and so on. Is that okay? Any more questions about the trace? Yep.
That's A under F.
Say that one more time.
The row F.
Row column F.
F, like after G, there is a F, right?
Yeah, this.
Yeah.
Uh-huh.
It's A.
Hmm?
The A under F.
Yeah.
This 5, you got it from E to A?
So f of A is still 5 because the f of something is the g of something plus the heuristic from that vertex to the destination. So the heuristic function of 5 has never changed. And the g value of A has to be a 0 because the g value of a vertex is the length of the shortest path from the start vertex to that particular vertex. But vertex A really is the start vertex. So by definition, the g value of A has to be a 0.
So this 5 is the heuristic value of A.
This 5 is the heuristic value of A itself, right? Because A is the start vertex. Yep. But it's not really that much of a concern because once A is not in the set O anymore, it can have the smallest or the largest possible value. It doesn't really influence the rest of the program because the only consideration is the choice of how we choose which vertex in O that we are going to explore next. But once A is not in that set anymore, it really doesn't matter. Okay. Any other questions? So normally, okay, if the heuristic function is a more reasonable heuristic function, then we'll be looking at a very few small number of exploration. This one is particularly bad because I made it so. Okay. Yep. Question.
Can we use the A-star algorithm to find multiple destinations like we did with X?
Um, I'm going to say yes and no. Okay. So by its very nature, it cannot do that because you have to designate one particular destination as the destination in order for the heuristic function to operate. But in reality, you may be able to coerce it to find the shortest path through multiple potential destinations, because what you can do is to list all the potential destinations over here and have all of them to merge to the superficial actual destination vertex with edges with a distance of 0. So they're effectively the same, but they are still represented differently. The difficult part is the heuristic function part is the difficult part, because the heuristic function doesn't really care about, oh, this is the heuristic function to this destination, this is the heuristic function or value to this particular destination. So it cannot take that into consideration. So that would be the really kind of tricky part is, how do you handle the heuristic function part? So as it is right now, I would say the answer is no. It cannot really easily handle multiple destinations. But you can probably change the way it operates, in order to accommodate multiple destinations. But that's going to be a separate topic. The trick has to do with the heuristic function. All right. But that's a good question. Any other questions before you start your long weekend? No other questions? All right, so you have your homework assignment. Okay, don't forget about the homework assignment that is due next Wednesday. Okay, so you have Monday to ask questions just in case you have any questions to ask. And then obviously after that one, we're going to have homework assignment for the A-star algorithm. So that means reviewing what we learned today and giving yourself examples to go through, would be also good things to do over the weekend. All right. Well, you guys all have a nice Thanksgiving. I will see you on Monday.